Hello, welcome to another module in this massive open online course. So, we are looking at examples to understand the framework or the mathematical framework or preliminaries required for developing the various optimization problems. Let us continue our discussion. In this module, let us start by looking at the eigenvalues of a Hermitian symmetric matrix. Okay, so we want to look at the eigenvalue decomposition or eigenvalues and eigenvalue decomposition of a Hermitian matrix. Hermitian symmetric that is, if a matrix is Hermitian symmetric, we know. So, this is our example number 5. So, recall matrix is Hermitian symmetric if A equals a Hermitian. Okay. So, m cross so for any m cross n. So, if A, remember this is for a complex m cross n matrix. So, and remember Hermitian is nothing but you first take the transpose of A and then take the complex conjugate. So, Hermitian involves two steps, transpose plus conjugate. So, first you take the transpose of a matrix, m cross n matrix becomes an n cross m matrix, and then you take the complex conjugate of each element. And if then you have a matrix which is A equals, satisfies the property that A equals a Hermitian, this is known as a Hermitian symmetric matrix or simply sometimes as a Hermitian matrix. Okay. And naturally for a Hermitian matrix, for a matrix to be Hermitian symmetric, it must be the case that it is a square matrix, correct. So, that an n cross n matrix remains an n cross n matrix when you take its transpose. Okay. So, this implies for a Hermitian matrix implies essentially also that matrix is square, makes sense only for a square matrix. Now, we want to prove some of the properties in this example. We want to prove some of the properties of this Hermitian symmetric matrices, that is eigenvalues of a Hermitian matrix are real. The first property is eigenvalues of Hermitian matrix are real. That is, if you look at consider the eigenvalues of Hermitian matrix, these are real. Okay. So, to prove this, let us consider x bar be the eigenvector of A, lambda equals the corresponding eigenvalue okay. Taking the Hermitian now what we are going to do is we are going to take the Hermitian on the left and right side. So, we have now Ax bar Hermitian equals lambda x bar Hermitian, and we will use the property that A be Hermitian, product of two Hermitian. So, A B Hermitian, that is the product of two matrices, and Hermitian, A B Hermitian is B Hermitian times A Hermitian. So, this implies basically that x bar Hermitian, that is Hermitian of vector x bar times A Hermitian equals x bar Hermitian times lambda Hermitian, but lambda is a scalar. So, this I can simply write as, and of course, this is just a number. So, I can simply write as x bar Hermitian into lambda conjugate, since lambda equals a scalar quantity, that is lambda is simply a number. So, for a simple number, the Hermitian of the quantity is simply taking the complex conjugate. Okay. And now we have this property x bar Hermitian A Hermitian equals lambda conjugate x bar Hermitian. Now we multiply on left and right by x bar. So, this implies x bar Hermitian A Hermitian x bar equals lambda conjugate x bar Hermitian x bar. But look at this x bar Hermitian x bar, this is norm x bar square. So, this is equal to norm x bar square lambda conjugate times norm x bar square, and further A x bar equals lambda times x bar. So, this implies x bar Hermitian lambda x bar equals lambda conjugate norm x bar square, and this implies, now lambda is a number. So, this is lambda x bar Hermitian x bar equals norm x bar square equals lambda conjugate norm x bar square, and from this, from the left hand side and right hand side, since x bar square norm x bar square is not equal to 0, this implies lambda equals lambda conjugate, which basically leads us to the conclusion that lambda is a eigenvalue of a Hermitian symmetric matrix. This implies that lambda equals a real quantity. Okay. So, eigenvalues of, so this implies eigenvalues Hermitian symmetric matrix are real. Eigenvalues of Hermitian symmetric matrix are real. Now, how about eigenvectors of a Hermitian symmetric matrix? Now, eigenvectors of a Hermitian symmetric matrix satisfy an interesting property, that is, eigenvectors of a Hermitian symmetric matrix corresponding to distinct eigenvalues are orthogonal, that is, their inner product is 0. We will demonstrate this fact. So, the property number 2, and another very interesting property, both these properties of Hermitian symmetric matrices are very interesting and have immense utility. The second property is that eigenvectors of Hermitian symmetric matrix corresponding to distinct eigenvalues. Corresponding to distinct eigenvalues, these are orthogonal, and this is a very important and interesting property. Okay. So, let us consider two eigenvectors xi bar comma xj bar. These are two eigenvectors, and remember, these correspond to distinct eigenvalues. Okay. these are the corresponding eigenvalues, and remember these are distinct, lambda I not equal to lambda j, that is these are distinct. Okay. And now what we want to show, that the inner product xi bar Hermitian xj bar equals 0, and the proof can proceed as follows. That is, if you look at A xi bar equals lambda I xi bar, and this implies, now if you take multiply by xj bar Hermitian, we have xj bar Hermitian A xi bar equals lambda I, or xj bar Hermitian lambda xi bar, which is basically lambda xj bar Hermitian xi bar. Okay, lambda xj bar Hermitian xj bar. So, let us call this as the first observation or the first result, xj bar Hermitian xi bar equals xj bar Hermitian lambda xi bar, which is lambda xj bar Hermitian xi bar. Now, we also have xj bar is an eigenvector corresponding to the eigenvalue lambda j, which implies axj bar equals lambda j xj bar. This implies that xj bar Hermitian, taking the Hermitian xj bar or axj bar, let us just write that one step, axj bar Hermitian equals lambda j xj bar Hermitian. This implies xj bar Hermitian A Hermitian equals xj bar, once again xj bar Hermitian, we have already seen lambda j conjugate, because lambda is once again it's an eigenvalue, it's simply a scalar quantity. So, this is lambda conjugate, but remember the eigenvalues of Hermitian matrix are real, which implies that lambda j conjugate equals lambda j. Okay. So, we will use that property here. This is equal to lambda times xj bar Hermitian, since lambda equals lambda conjugate, and this implies that, well, again realize that this is the Hermitian symmetric matrix, A Hermitian is simply A. Okay. So, we have xj bar Hermitian into A equals lambda conjugate into xj bar Hermitian. This implies that now if you multiply by xi, I am sorry, this is lambda. Now, if you multiply by xi bar, we have xj bar Hermitian A xi bar, I am sorry, this is lambda j, this is lambda j, this is lambda j, this is equal to lambda j times xj bar Hermitian, lambda j xj bar Hermitian xi bar. Okay. So, xj bar Hermitian xi bar equals lambda j xj bar Hermitian xi bar, and this we can denote as result 2. And now, if you see from result 1 and result 2, xj bar Hermitian A x bar xi bar equals lambda, or lambda, in fact lambda I xj bar Hermitian xi bar. Similarly, if you look at result 2, xj bar Hermitian A xi bar equals lambda j xj bar Hermitian xi bar. So, this implies from 1 comma 2, from results 1 comma 2, what we have, this implies, well, this implies lambda I xj bar Hermitian xi bar equals lambda j xj bar Hermitian xi bar, which implies now lambda I minus lambda j into xj bar Hermitian xi bar equals 0, and now since lambda I not equal, remember that is a key point, lambda I is not equal to lambda j, otherwise lambda I minus lambda j can be 0. So, this implies xj bar Hermitian xi bar this equal to 0. So, this finally verifies the fact that eigenvalues eigenvectors corresponding to distinct eigenvalues are basically real. Okay. So, the eigenvalues corresponding to the distinct eigenvalues are basically real. Okay, let me just mention this, or eigenvectors corresponding to distinct eigenvalues are orthogonal, that is what I meant to say. Eigenvalues corresponding to distinct eigenvalues are eigenvectors corresponding to distinct eigenvalues are orthogonal for a Hermitian symmetric matrix. Okay, and these are two important and interesting properties of Hermitian symmetric matrices that one uses frequently during the development of various techniques for optimization. Okay, all right. Let us look at another example. It's example number eigenvalue decomposition of Hermitian matrices. Eigenvalue decomposition of Hermitian matrices. For a Hermitian matrix, that is, consider that is n cross n complex Hermitian matrix equal to a Hermitian, that is Hermitian symmetric. Let the eigenvalues be equals are the eigenvalues and V1 bar, V2 bar, Vn bar be the corresponding eigenvectors. Okay. Now observe that let these eigenvectors be unit norm. Okay. We can simply normalize, remember an eigenvector, if you normalize it, it still remains an eigenvector because you are simply dividing it by its norm or by a constant. Okay, that is you are simply scaling an eigenvector. Okay. So, let us consider the eigenvectors to be unit norm. All right. So, let norm V1 bar equals norm V2 bar equals norm Vn bar. This implies eigenvectors equal to unit norm. And further from the property previously, let us assume that the eigenvalues are distinct, which implies Vi bar Hermitian Vj bar equal to 0 for I not equal to j, that is, if the eigenvalues are distinct, then the eigenvectors satisfy the property Vi bar Hermitian Vj bar equals 0. Okay. Now notice that if you consider this, observe that if you consider this matrix V1 bar, V2 bar, Vn bar, the matrix of eigenvectors. If you now perform V Hermitian V, then what you are going to have is you are going to have V1 bar Hermitian, V2 bar Hermitian, Vn bar Hermitian times V1 bar, V2 bar, Vn bar, which is equal to, well, if you look at V1 bar Hermitian V1, that is 1, V1 bar Hermitian V2 is 0, V2 bar Hermitian V1 is 0, V2 bar Hermitian V1 is 1. So, this you can see is simply the identity matrix, which implies V is the inverse of V Hermitian and V Hermitian is the inverse of V. So, we have, well, we have something interesting. What we have is, we have V Hermitian V. So, we have V Hermitian V equals identity implies V equals V Hermitian inverse, and since the inverse of a square matrix is unique, and this also implies V Hermitian equals V inverse, and this also implies that since if A is B inverse, AB is identity, BA is also identity, this also implies that V Hermitian equals identity. Since if AB is identity, then BA is also identity for square matrices. Okay. Okay, so, we have, and such a matrix V which satisfies V Hermitian equals V Hermitian V equals identity, such a matrix is termed as a unitary matrix. So, V is termed as, this satisfies this interesting property, that is termed as a unitary matrix, that is V matrix V, a square matrix which satisfies this property V Hermitian equals V Hermitian V equals identity is termed as a unitary matrix. Okay. Now, let us look at the product A V, A times matrix V, that is A into the eigenvectors V1 bar, V2 bar, Vn bar. You can see this is nothing but this equals, well, A V1 bar, A V2 bar, A Vn bar which equals, if you look at this, but these are eigenvectors. So, A V1 bar is lambda 1 times V1 bar, A V2 bar is lambda times V2 bar, A Vn bar is lambda n times Vn bar. These are the various columns which you can now write also as, remember we are looking at A times the matrix V. So, A times the matrix V equals, now you can write this as V1 bar, V2 bar, Vn bar times the diagonal matrix lambda 1, lambda 2, lambda n. This is a diagonal matrix. So, this is nothing but your matrix V, and this we denote by the matrix capital lambda, which is the, let me just write it with a little. So, this we denote this by the V, and this is basically your capital lambda. And what is this? This is the diagonal matrix of eigenvalues. This is the diagonal matrix of eigenvalues. So, we have A times V equals V times lambda, multiplying on both sides by V Hermitian, A times V Hermitian equals V lambda V Hermitian. This implies the matrix A which is Hermitian symmetric, can be expressed as V lambda V Hermitian, where V is the matrix of eigenvectors and lambda is the diagonal matrix of eigenvalues. So, what is V? V equals the matrix of eigenvectors, lambda equals diagonal matrix of lambda equals diagonal matrix lambda equals diagonal matrix of eigenvalues, and this is termed as the eigenvalue decomposition. This is termed as the eigenvalue decomposition. Okay, eigenvalue decomposition of A, and this has many interesting properties. For instance, if you want to compute the square A into A, which is equal to A square, this will be equals, you can write it in terms of V lambda V Hermitian into V lambda V Hermitian, which is equal to, now V Hermitian is identity, so which is equal to V lambda lambda V Hermitian equals V lambda square V Hermitian. So, this is A square. Okay. Similarly, you have many other interesting properties. For instance, you can generalize this as A raised to n for this Hermitian symmetric matrix is V lambda n V Hermitian, and lambda to the power of n is easy to compute because since it is a diagonal matrix. So, all it is, it contains lambda I, each lambda I raised to the power of n on the diagonal. So, lambda raised to the power of n, this is very easy to compute. This is simply the matrix. If you think about this, this is lambda 1 to the power of n, lambda 2 to the power of n, so on lambda n. I am sorry, I should have used a different integer here, lambda m, lambda n raised to the power of m. Okay. So, this is simply raised to the power of m, raised to the power of m, raised to the power of m. So, this is easy to compute. And frequently you will see this is a very interesting property, as well as this is a very handy tool to perform several matrix manipulations, that is eigenvalue decomposition of a matrix. Alright, and it is also one of the fundamental decompositions of a matrix, or one of the, what you can also call it as one of the fundamental properties, or one of a matrix. Alright, so we will stop here and continue with other aspects in the subsequent modules. Thank you very much.